Hey class, this is Adrian. I wanted to go ahead and make a couple videos. As you probably learned on the first day or two of class, with Blackboard and other things, and through the syllabus, I did have a statement that I am going to be out at least a couple weeks, probably 4 weeks throughout the semester. Let me pull up the syllabus real quick and I'll just kind of point that out. However, since I'm going to be out, you will notice during the weeks of 24 to 26 August and 5 to 7 October, I wanted to go ahead and record a couple of class sessions so you would have that information at your disposal while I am out of town. I really hate to miss this first week of classes, especially, but work has got me doing that, so I don't really have a lot of choice. So what I've done, or what I'm planning to do, is you can log into the course shell here, and you see first week of class stuff. Made a video for that earlier, but if you go under course content, and our first section, actual section we're going to cover from the book is section 4.1. So that's what this session is going to cover. I will record a couple more sessions probably for 4.2, maybe even 4.3, and maybe throughout the semester I'll go ahead and record some lectures on that. But if you go to handouts and lectures, you can see the different sections here. Here's 4.1, angles and radians measure. So we're going to look at that, and if you click that handout 4.1, you'll see there's other versions of notes through different semesters that I've recorded. But section 4.1 is where we're going to start. I've got that pulled open in OneNote so I can kind of save my notes off, but you're able to pull these up, you're able to print these out if as needed. And I'm going to kind of base the section off of this handout, and I'm going to go relatively quickly. I don't want to take too long. I made a video for these sections a couple times in the past, and it seems like I get a little distracted and get going a little too slowly. So I just want it to be kind of an overview. Some of this I'm sure you can go in and learn on your own. So I'm going to go ahead and get started though. We're in section 4.1 here, angles and radian measure. I'm going to go ahead and get my stylus ready here. So in this section, we're really going to start with just kind of a definition of what radian measure is, what angles are, and most of you, I'm sure, are familiar with what angles are. But as far as angles, we're going to look, for example, at the hands of a clock. The hands of a clock make an angle, and there are really a couple different angles you could look at with the hands of a clock. But you could think of each of these lines, these hands of your clock, as being what's considered a ray. It's just a line has an endpoint and it extends infinitely in the opposite direction. Now the angle is kind of a way of measuring this amount between the two rays. Okay. Now, if you look at where those two rays meet, that is considered the vertex of your angle. Okay, now again, most of you already understand all this, so it's not that big of a deal. Now for this class, we're really going to look at angles in what are considered the standard position. Now for standard position, at least in this class, we're going to think about the vertex of the angle is going to be at the point 0, 0. So if you look, and I'll try to kind of sketch this out here. If I had a coordinate system here, here's your y-axis, and we can draw an x-axis in here. Not perfect, but just to give you an idea. So there's your x-axis. Here's going to be 0, 0. That's going to be the vertex of any angle that we draw in here. So that's going to be the vertex, and our initial side of our angle is going to lie on the x-axis in the positive direction. So that's going to be the initial side of all of our angles as we consider them. So any angle that I draw, I'm going to go from this kind of 0, 0 origin in this initial side, and I'm just going to kind of say, all right, let's just sweep out an angle, and I'll just kind of say right here, for example. That's some angle, and I'll say my terminal side, for example, would be right there. So that angle, we'll say alpha, that is an angle that is in standard position. Now, obviously, you could have that same angle that's not in standard position, right? You could have something, that would be, maybe your initial side would be here and your terminal side might be here. So it's kind of the same amount of angle here. It's just rotated slightly. But for this class, like I said, we're just going to really consider this kind of standard position. So we're going to start with the positive x-axis, and we're going to go counterclockwise, and that's going to give us a positive angle. Now, if we go clockwise, that's going to be considered a negative angle. So as I circle the vertex of the following angle, so again, that's going to always be, at least in standard position, that's going to be this 0, 0 point. And it says positive x-axis, the other ray represents the terminal side of the angle. So angles are really measured by the amount of rotation to get to the terminal side of our angle. Now, most of you are probably more familiar, at least, with a measure called degrees. So you've probably heard of, moving around in a circle. That is 360 degrees. So if I started, at standard position here, and here's my initial side, and I go completely all the way around in the positive direction, that would be 360 degrees. That gets me back to where I started from. So if you think about that, there's other ways to kind of recognize angles. If I said, well, what if I didn't go all the way? If I go all the way around, I am at 360 degrees. So if I only go halfway around, right? So if instead I just kind of go here, that's going to be half of 360, or that's going to be 180 degrees, right? So in other words, if I'm standing here and I turn completely and face the opposite direction, then that would be I've turned, I've done a 180. I'm facing the opposite direction. So if I wanted to take half of that, for example, right, then that would be a smaller angle. This is another important angle we'll talk a lot about. That is considered a 90-degree angle, or you might have heard of what's considered a right angle. Okay, so those are a couple of examples. And if you recall, maybe from geometry, an acute angle means it's less than 90 degrees, or so an 80-degree angle is an acute angle. If it's greater than 90 degrees, it's considered obtuse angle. Right? So if it's a 150-degree angle, that's an obtuse angle. Now remember, you can represent anything as less than 180 degrees, right, by just going the opposite direction. That's really a separate discussion, but anyway, a couple other angles that I pointed out here. 180 degrees, we've already talked about that one. 270 degrees. So if we look at kind of our coordinate system here, you get an idea, and again, somewhat of a review. So all the way around, that's 360. So halfway around, that's half of that, which is 180 degrees. And of course, we kind of talked about it. If I only go half of that, then that's going to be your 90-degree angle. So the last one that we've kind of got here says, all right, this is 90, this is 180. So in other words, I'm adding 90 degrees every time. So 90 plus 90 is 180, 180 plus 90. That would be I'll try to draw this in here, not perfect, but that's going to be a 270-degree angle, right? 180 plus that 90 degrees. Okay, so those are kind of just, if you look at all four directions starting from the origin, you've got 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. So that gives you an idea in degrees. Another way you can measure angles is through a different way of measuring. It's called radians. Now, a radian is really measure of a central angle of a circle that intercepts an arc length that is equal to the radius. So what it really gets to is the radian measure is kind of a ratio between S here. Let me change colors back here. That S is considered your arc length. It's a ratio of arc length to radius. So you have a circle. If you sketch out an arc length of, S, and your radius is R, that theta is in radian measure at least. That gives you what your angle is in radians, right? So you can kind of see that over here. Here's an example. If I look, here's my arc length. Now, if that arc length is the same as my radius, guess what? That's 1 radian. So in this case, this theta equals R over R, so it would be 1. That would be 1 radian measure, and we'll look at that at some point. But a central angle theta. So here's an example. Here's our formula. We're going to use theta, and remember this is theta in radians, not in degrees, is equal to that ratio of arc length to radius. So central angle theta in a circle of radius 12 feet. So that's going to be important. Intercepts an arc length of 42 feet. So those are our two measurements. So if I wanted to know the radian measure of theta, I would say, well, theta equals, again, S over R. Now, S was our arc length, and I'm giving you that. That is 42 feet. And our radius is 12 feet. So that would be, again, I have common terms here, feet and feet. So those kind of cancel, and you have 42 over 12. So you could leave it like that. We'll go ahead and let's say 42. I know I can at least divide by 2, right? That's 21 over 6. So I can divide both of those by 3. So that'd be 7 over 2 radians. Okay, so that kind of gives you an idea of what radian measure is. This is really 3.5 radians. Now you could also think about what that is in degrees. We'll get to that. But we're just kind of talking about how you can use this formula for arc length and radius to kind of get you some measures of angles here. So we'll try to speed up. We're about halfway through where I wanted to be or more. So I'm going to try to speed up a little bit. So we'll have notes online, and hopefully we'll go through some of this in class as well. So the circumference of a circle, though, you might have heard of this. If you look it up, you can Google it, is given as C equals 2 pi r, where r is the radius. So if that's the case for the circumference, now circumference, remember, that's really kind of the same thing as arc length. So what is the radian measure of a complete circle? Well, I'm going to come in here and say, all right, arc length, I covered that thread. So my arc length of a complete circle, at least, is 2 pi r. So that's really the same as your S for a complete circle. So my theta is going to equal 2 pi r over, again, the radius of my circle. Well, the radius in this case is just r. Well, 2 pi r divided by r, well, those r's cancel. So that means the radian measure for a complete circle is 2 times pi radians. Okay. So I know one thing now. If I have a circle, if I'm looking at my angles and I make a complete circle, we already knew that was a 360-degree angle. Well, I also know now that that's equivalent to a 2 pi radian amount of angle. So those two terms are really the same thing. 2 pi radians is the same as 360 degrees. Well, guess what? If I go halfway around a circle, I know that's 180 degrees. Well, in radians, if I go all the way around, it's 2 pi. If I go halfway around, guess what? It is pi radians. So we're going to use that one. That's the one you see more often because you don't have to simplify as much. But we're going to use that really ratio of radians to degrees to convert back and forth. So to convert from degrees to radians, you're going to multiply your degrees by pi radians over 180 degrees, or pi over 180. And the way I remember this is that pi is in the numerators, because that's what you want to kind of, most of your radian measures will usually have a pi involved, at least the ones we're going to be discussing most of the time. So for all of these next 4 examples, and I'll do a couple of these and probably move on so we have a little bit more time, but 60 degrees to radians, I want to multiply that by pi over 180. And the reason, another way you can remember that is if I want to get rid of degrees. So this is 180 degrees. So really those degrees are canceling out. And I'm going to be left with this radian measure here, right? So when I do that multiplication, that's going to give me radians and cancel out the degrees. So you could do that multiplication and then simplify, or you could notice, hey, this is 60 over 1 times pi over 180. Well, before I multiply, 60 goes into 60. one time, and 60 goes into 180 three times. So I would be left, in this case, with pi over 3 radians. So 60 degrees is the same as pi over 3 radians. Okay. If I wanted to go 270 degrees, I would just really do the same thing. I'm just going to multiply by pi over 180. And again, I want to simplify before I multiply rather than multiplying and then trying to simplify. But I know 90 goes into 270 three times. 90 goes into 180 two times. So if I do that multiplication now, I'm left with 3 pi over 2 radians. Now, I don't always write radians. You'll notice sometimes the homework will not necessarily look for that either. If nothing's written there, I'm going to consider that it is radians. If you have a degree symbol, then that's going to be my indication that you're talking about degrees. I think the homework's going to kind of do the same thing. Anyway, so the next one, very quickly here, times pi over 180 because I am going from degrees to radians. So let's see, 60 goes into 300 5 times. 60 goes into 180 3 times. So that would give me negative 5 pi over 3 radians. I'll leave it blank this time, but I usually do that right. And then finally, just again quickly, 30 degrees times pi over 180. 30 goes into 30 one time. 30 goes into 180 6 times. So we get pi over 6 radians. Now this is another, a couple of these are pretty common. One is this 60 degrees to pi over 3. That is kind of one that you'll probably figure out eventually. Another one is 30 degrees is the same as a pi over 6 radian angle. Okay. All right, so now we're going to do the opposite. I want to go from radians to degrees. Well, that's easy enough. Instead of multiplying by pi radians over 180 degrees, now I want to get rid of radians. So I'm going to put my pi radians right in the denominator. So I'll put my 180 degrees on top. So again, radians are effectively canceling out here. And again, 180 over pi, guess what? 180 degrees over pi radians, that's the same as multiplying by 1, right? Because that's an equivalent measure. So pi over 4, if I cancel out those pi's, let's see, 4 goes into 4 one time. 4 goes into 180 degrees, what, 40, right? Because that'd be 16, 20, so 45 degrees. And again, my radians here are going to cancel out. So I'm going to be left with 45 degrees, right? So that's the same as pi over 4 radians is the same as 45 degrees. And you could figure that out kind of like we did earlier, right? Half of 180 degrees is 90 degrees. Half of pi would be pi halves. Half of that would be pi over 4, etc. So that's another one. And again, so anytime we're going from radians to degrees, we're going to multiply by 180 degrees over pi radians. So let's see, pi terms cancel. 3 goes into 3 one time. 3 goes into 180 60 times. So I would be left with negative 240 degrees in this case. The next one I find kind of interesting is 1 radian, which we don't see a lot, but just so you know, in degrees, I would do the same thing. I would multiply by 180 degrees over pi radians. And I usually have you leave pi in your answers. You'll notice here I've got pi here, pi in all those answers. But here, when I'm converting to degrees, I'm going to go ahead and get rid of pi as a term. So my radian terms cancel, right? Radians and radians. So I'm going to have 1 times 180 divided by pi. Well, let's think about what that is. And I'm going to pull up a calculator here. So give me just a second. I should have had this pulled up. But if I want to multiply, or I want to divide 180 divided by pi, and I get 57.295 or 57 point, we'll say 3. So that's about 57.3 degrees. Again, not something you see super often, but 1 radian is 57.3 degrees. Kind of interesting. And then finally, pi over 2, again, 180 over pi to get to degrees. So the pi terms would cancel. 2 goes into 180, 90 times. So you would have 90 degrees. Now, again, I went through those fairly quickly. I did want to kind of get on to some other stuff here. But that's how you're going to convert between radians to degrees, degrees and radians. And you'll see this on quizzes and other assignments now and probably later on in the semester. Okay, now we can convert angles from radians to degrees, which we've just done. And some people like to do that. But a lot of times it is helpful to just consider where angles are in a radian sense in standard position. So some of these I think are pretty self-explanatory, right? If I think about 2 pi, well, that's basically saying I've done a complete circle, so that's not too bad. And so 2 pi would be your complete circle. That's your 2 pi angle measure. If I wanted to do half of that, right, that would be my pi angle measure. Right? Well, if I take half of that, guess what? I'm just going to take half of that angle measure, so that would just be up to this point. So that would be a pi over 2 radian. So if I go 3 pi over 2, well, that one's a little more interesting. If this is 1 pi over 2, that would be 2 pi over 2. That would be 3 of them. So three little segments here, 45 degree or 90 degree segments here. So this one down here, I guess if you were to extend that, that would be your 3 pi over 2 radian angle. Okay, so given that and kind of using that, we can draw and kind of label each angle in standard position. So the first one I've got here is theta equals pi over 4. So I think that one's pretty self-explanatory. So try to sketch this a little bit neater down here maybe. A pi over 4 radian measure, right? So from our initial side here, right, this is your 0 degrees or 0 radians, same difference. If I go up here, it's pi over 2. So if I take half that, right, half of pi over 2, well, let's just think about that. Pi over 2 divided by 2 is the same as pi over 2 times 1/2, right? The reciprocal of the bottom, which is 1 over 2 instead of 2 over 1. So you're going to get pi over 4. So that's what your pi over 4 radian angle would look like. It's going to be just that. Basically, you're just taking that angle and just splitting it in half, taking that 90 degree angle. Pi over 2 angle. So 3 pi over 4, well, this is pi over 4. Now we'll come in here and say, all right, this would be 2 pi over 4 if I go another one, or pi halves. So if I go 3 pi over 4, guess what? I'm going over to this angle, right? So that would be your 3 pi over 4. So you kind of see how we split that into little pi over 4 segments. The next one is negative pi over 4. So here, instead of measuring, from here in a counterclockwise direction, we're going to go the opposite direction, but it's the same amount of angle. So we're going to go this direction. That would be your negative pi over 4. Okay. The next one's really kind of interesting. Is beta equals negative 2 pi divided by 3. Well, that one we got to think about a little bit. So if I go all the way around again, that's going to be in the positive, counterclockwise direction. It would be pi radians, right? 180 pi. If I go the negative direction, though, this would be a negative 180 or a negative pi radian measure. If I go all the way around. Well, I don't want to go all the way around. I don't want to go halfway around. I want to go 1/3 of the way around. So I don't want to go quite to half. I want to be somewhere in here. So I want to be about 1/3. So if I were to take this segment, so let's just kind of pretend here you've kind of got this pizza here, and I want to divide it 3 ways. So I'm going to come somewhere in here, it looks like. Right? So what I'm really trying to get to, I guess, is that this angle would be the same as this angle would be the same as this angle. It might not be perfectly drawn here. If I did that, divided that into thirds, right? So this would be negative pi over 3. If I go another one, that would be negative 2 times pi, negative 2/3 of the way. And then I go all the way around, it'd be negative 3 pi over 3. So it's really this one, right? Negative 2 pi over 3 is what I wanted to get to. So that's kind of the angle I was trying to get to here. And that might be a little confusing. I'll try to explain this, a lot of this a little bit better in class when I get a chance. But hopefully that helps. Negative 2 pi over 3. So really what we're doing is we're taking kind of our coordinate system and we're just dividing it up into different manners. So we're going to say one way we've kind of divided this up is we've said, all right, we've already got it split up into 4 ways, right? So here's pi. Here would be 0 or 2 pi. So if I take half of that, right, if I go all the way around, take half that, it's pi. If I take half of pi, I'm at pi halves. If I take, 1 pi half, 2 pi half, 3 pi halves. So we've kind of got that. Now there's different ways of splitting this up from here. The first couple ways we did it, we said, all right, let's take each of these and just cut them in half. So if I do that, I'm kind of splitting this up into fourths. Right? So I would have pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi, So you could come in here really at each of these. This would be it at 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which is the same as 3 pi half, and 7 pi over 4. So in this drawing, at least, we've split it into fourths. Well, that's really kind of interesting. We could do that again, right? We could split that in half, and we could have this split into pi over 8, 2 pi over 8, 3 pi over 8, 4 pi. So you could keep going that way. But again, pi over 4 is pretty common. Another common is what we just did a minute ago, and that is to kind of say, all right, let's split it into thirds. So this would be kind of your pi over 3. All right, so if I kind of do the same thing here, and I split that into, so this would be pi over 3, 2 pi over 3. If I kept going, 3 pi over 3. Keep going, that's another 4 pi over 3. 5 pi over 3. And I got all the way back around. Guess what? 6 pi over 3. So we're just splitting it up again. That way split a little bit differently. So that's another common way you'll see it is over those pi thirds. And then finally, you'll see that split a lot of times into, you say, all right, take pi over 3 and divide by 2. Well, that's pi over 6. So that's another way you'll see it. Right? So that'd be pi over 6, 2 pi over 6. Right? If I get another half of that, right? And then I would have 3 pi over 6, 4 pi over 6, and, come in here about half of that, 5 pi over 6, 6 pi over 6, right? So you could split it into sixths as well. And I don't really like where I drew this line. I'm going to redo that one, I think. So what we're trying to do is kind of take this pi over 3 and split it in half. So it's really a little further up there. Okay, so I know that's kind of hard to follow. I think this will make more sense when I try to cover this a little bit more in class, but hopefully that gives you an idea. And this video is already almost 30 minutes, so it's going way longer than I anticipated, so I apologize for that. And then finally, you got 13 pi over 4. Well, if you think about that, right, we've just been talking about splitting this up, pi over 4, 2 pi over 4, 3 pi, 4 pi, 5, 6, 7, 8. So this 2 pi, right, so that's really the same as 8 pi over 4. Well, I'm at 13 pi over, so I gotta go 5 more, right? So if I keep going, that would be 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, 13 pi over 4 should be right here. So we'll kind of sketch this in here just to kind of show you what I mean. Okay, so once we've gone all the way around, we've gone 8 pi over 4, right? So if I keep going, 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, 13 pi over 4. Okay. Another way you could have looked at that, well, this is 2 pi, right? If I go all the way around. So if I go another part of the way, that'd be 3 pi, which would be 12 pi over 4, right? 12 if you think about fractions. So one more would be 13 pi over 4. Okay, so two angles with the same initial and terminal sides but could be, they're considered what are called coterminal angles because they have the same initial and terminal sides. But you might get to those in different ways, right? A 90-degree angle, for example. If I think about what a 90-degree angle is, that's this angle here. That's what we're talking about, actually. Let's come in here and do this. Here's a 90-degree angle. Well, a negative 270-degree angle, that'd be 90, 180. Has the same initial side, same terminal side. So those are coterminal angles. Pi over 4 and 9 pi over 4. Well, just kind of talk to a similar example. Pi over 4 is just kind of splitting the difference here, right? This is your pi over 4. 2 pi over, or I'm sorry, 9 pi over 4 would mean I've gone 8 pi over 4 and then another pi over 4. So again, same initial and terminal sides, just a different way of representing them. So we can use that. We can say, all right, find a positive angle that's less than 360 degrees that is also coterminal with a 400-degree angle, then a negative 135. So the way we're going to do that is if it's greater than 360, if I just subtract 360 degrees from that, you have 40 degrees. Well, that kind of makes sense, right? So if I just if I'm if I'm at 40 degrees, for example, I'm at some angle here. I started at 400 degrees, right? So if I started right here, that's my 400-degree angle. So if I subtract out a complete circle from that, so I say, all right, let's start here. Let's subtract out just that part. Then I am left with that part. Okay, so it is a 40-degree angle. So if you subtract or add 360 degrees to a degree measure, you're at the same exact point that you started with. Makes sense, right? If you're standing point in one direction, you do a 360, then you're facing the same direction. If you do 360-degree turn 5 times, you're still pointing in the same direction. So if I have a negative 135 degrees, guess what? I want it to be positive. So I'm going to add 360 degrees to it. So to do that, let's see, 10 minus 5 would be 5. 6, 5 minus 3 would be 2. And 3 minus 1 would be 2. So 225 degrees if I subtract 135 from 360. Okay? Okay. So we're gonna keep going with this. Again, I'm sorry I'm kind of speeding up here towards the end. We'll review some of this. But it says find a positive angle less than 2 pi that is coterminal with. Well, if I'm in radians, I can't use 360 degrees anymore, but I can use 2 pi, right? So I want to be less than 2 pi. In this first term, at least, I have 5 as my denominator. So 2 pi, if I want that to be equal to something over 5, uh, something to have a denominator of 5. Well, if I need 5 in the denominator, that means I could multiply this by 5 over 5. and you get, you get 10 pi over 5. So I need something that is less than 10 pi over 5. Well, 23 pi over 5 is not it. But I can subtract 2 pi from that. Or that's really the same as saying 23 pi over 5 minus 10 pi over 5. And I would get 13 pi over 5. Well, that's still not less than 2 pi, which we said is 10 pi over 5. So I'll subtract 10 pi over 5 from that again. So we end up with 3 pi over 5. So that is a positive angle, and it is now less than 2 pi. We could kind of think about that again here. I could say, well, negative pi over 15. I could come in here and say, well, let's add 2 pi to that. Well, that's going to be the same as negative pi over 15 plus, well, 2 times 15, that'd be 30 pi over 15. That's the same as 2 pi. So that would be 29 pi over 15. Again, that's less than 30 pi over 15, so it's less than 2 pi, but it is also positive. Okay, so let's move ahead. It says we can use the formula for radian measure discussed above. Well, we can derive a new formula for arc length. So again, this was your angle in radians. S we said was arc length. And then R we said was the radius of your circle. If you were to draw one there. Okay. So it says find a new formula for arc length. So I want to solve this for S. So if I take theta equals S over R and I want to solve for S, I would multiply both sides by R. When you do that, these R's cancel and I get S equals and then R times theta, where theta again is in radians. So we're going to use that, S equals R theta. Just a reordering of what we had earlier. It says consider a circle with radius of 6 inches. Find the length of the arc intercepted by an angle of 45 degrees. Sounds easy enough. Express arc length, turns of pi, etc. We'll say S equals R theta. Well, we know some of this information. We know the radius, that's 6 inches. Well, that's easy enough. 6 times. And then theta, well, it gives us an angle of 45 degrees. But, again, very careful here. That is in degrees. Angle theta has to be in radians for this formula to be true. So I have to think, well, 45 degrees in radians, I need to multiply that by pi over 180. Okay, so 45 goes into 45 once, it goes into 180 4 times. Yep. So I get pi over 4 radians. So that's what I need to use here is pi over 4. So now I can multiply that out. Let's see, 2 goes into 6 3 times, 2 goes into 4 2 times. So I get 3 pi over 2. It's not radians anymore, right? Because it's inches times radians. Okay, so my arc length is going to be in inches. Okay. All right, so 3 pi over 2, it says expressed in terms of pi, then roundly answer to 2 decimals. So we'll do that. Let's just see, what is 3 times pi divided by 2? 3 times pi. And I want to divide that by 2, and I get about 4.71 inches. Okay. And so we can kind of use this formula. So really, the last thing that we discuss here is really talks about a satellite. I'm flying in circular orbit, elliptical orbit, really, I guess, around the Earth and its shadow on the surface as it rotates. So I have this satellite here, right? And it's flying around up here. So in space, I'm flying, you can look at S2 here. That's my arc length of that one. And then you can look, down at its shadow on the Earth. Well, this amount of arc length that I'm flying out in space is considerably, well, sometimes considerably, is more than its shadow, right? And as you get closer and closer, I guess, to the center of the Earth, it's quite a bit more. Um, so my speed, right, if I'm traveling this amount of arc length in space compared to the shadow, well, you'd think, well, my linear speed, the amount of arc length that I'm covering, linear distance versus time is greater. So the linear speed is that in space, but its shadow is going to be a little bit smaller. Well, if you think about something, a different term way of thinking of this is just what is this angle, right? I'm sweeping out this angle. I'm covering the same amount of angle in space as the shadow is on Earth. So the angular speed looks at the amount of angle that is traversed versus time. So in this case, the angular speed is exactly the same for the satellite in space and the shadow on Earth. So another way of thinking of this, and again, we'll look at some other examples here. If a point is in motion on a circle, radius r through an angle theta, so the linear speed is given by this. V equals s over t. S is arc length. Again, arc length we talked about earlier. We can express that as r times theta. The angular speed is considered theta divided by t. Angular, again, is theta is in radians. Okay, so we're going to use those definitions. It's kind of a simple example, kind of neat. The Disneyland Ferris wheel has a radius of 75 feet. So I'm going to go ahead and note that. That's r. The wheel rotates at 2 revolutions per minute. Find the linear speed, not angular, in feet per minute of a seat on this Ferris wheel. Well, it's 2 revolutions per minute. So we kind of already know a little bit about the angular speed. So we're going to look at the linear speed, right? So how much air, how much arc length am I covering over time? So V equals S over T, right? That's our linear speed formula. Well, S we said was R theta. I know R. I got to figure out what theta is. Well, 2 revolutions per minute. Okay, well, what is 2 revolutions? Well, in degrees, you'd think, well, that's 360 times 2, so it'd be 720. But in radians, that's 2 pi twice. So that'd be, I guess, 4 pi. It's really 2 times 2 pi, right? So you're going to have 4 pi radians per minute. So my formula down here, you can see, all right, V equals R times theta. So R is 75. My amount of theta, my angle, is 4 times pi. And time, it says feet per minute. And I'm giving this in revolutions per minute. So that's per minute, right? 1 minute, I guess. So you could calculate that. 75 times 4, I believe, is 300 pi. Revolutions, I guess, right? I'm sorry, feet. I'm sorry, arc length, right? So it's 300 times pi feet per minute. So you're traveling that amount of feet per minute. So that's kind of one way to look at it. Let's see on the calculator, what is 300 times pi? So 300 times pi equals 942.5. Again, that's feet per minute. It sounds like a lot, really. But again, that's per minute, not per second. If you wanted to look at that per second, then you would say, well, that's per minute. So if I divide that by 60 seconds, then I would give me an idea of how many feet per second. So just out of curiosity, divide that by 60, I get 15.7 feet per second. So that sounds like quite a bit, really. So if you think about it, that Ferris wheel's is scooting along pretty good as far as arc length is concerned. Anyway, so those are some examples. We'll go through this. Hopefully, this one, especially this first section, we'll cover this in class to some detail that first day. The next week when I'm out, you can look at this video. There are older videos as well, I think, of this section, so you're welcome to go through those. So just to point that out. Again, if you go to the content here, you'll see there are all kinds of notes. If you go back a couple of sections here, 4.1 angles and radian measure. Oh, sorry. Go back here, chapter 4. Class session videos. I'll put this under here, but you will also see, hey, guess what? I have videos from past years as well. So went a little long today. So you going back to review those might be a little bit shorter. So that might be an option as well. But anyway, so again, apologize. This went about the length of an entire class. So I will try to make these shorter in the future. But hopefully this is helpful, and I will talk with you guys next time. Hope you have a good week.